Imagine you're deep in the ocean commanding a submarine. Your mission is simple: survive and make it back to base. But there's a problem. An enemy submarine is hunting you armed with nuclear torpedoes. To make matters worse, ocean currents are constantly shifting your position, and your sensors, they're far from perfect, feeding you noisy and unreliable data. So, how do you figure out where you actually are? More importantly, how do you predict where the enemy is and where their missiles might strike? This is exactly the kind of problem the Kalman filter is designed to solve. But rather than bombarding you with equations right away, we're going to build up to it, step by step, so you can truly understand what makes it so powerful. And we'll start with learning about why recursion is important. So how do we usually calculate an average? Simple. We add all the terms in a set and divide by the number of terms. But there's a problem. Calculating the average this way becomes computationally expensive when dealing with large amounts of data. In a high-stakes scenario like our submarine, we need a faster and more efficient method to process information in real time. This is where a recursive definition of the average comes in. So let's derive it. In this notation, we have x bar sub k minus 1, meaning the average exactly one k step before x bar sub k. If we multiply both sides by k minus 1, we get this expression. Referring back to our definition of the average x bar sub k, and we multiply both sides by k, we get k x bar sub k equals this expression. And we can spot that k minus 1 x bar sub k minus 1 is in this expression, so we substitute that in. And now if we divide both sides by k minus 1, we get the following expression. And finally, to isolate x bar sub k, if we multiply both sides by k minus 1 over k, we get x bar sub k equals k minus 1 over k times x bar sub k minus 1 plus 1 over k xk. Now we have a more efficient way to calculate an average. By using recursion, we can update our current average based on the previous one, eliminating the need to recompute everything from scratch. This idea is fundamental in the Kalman filter, which relies on past data to make predictions and refine estimates. Before we move on, we should call k minus 1 over k as alpha sub k so that we can say alpha sub k equals 1 minus 1 over k and 1 minus alpha equals 1 over k, just to help with notation. Now what we have just done is called the average filter, and it works great for noisy data that is meant to converge at a single point, which is not totally useful for our submarine. Remember, we are constantly changing states and our variables are not constant. This is why we need to include something called the moving average. To effectively track a changing signal, we need a moving average. Unlike a standard average, which considers all past data, a moving average only includes a fixed number of recent data points, denoted by n, which we can adjust. This equation tells us that the kth data point, we compute the average of the previous n points. When written in a recursive form, it becomes this expression. This reformulation of the average filter allows us to compute the new average efficiently without resumming all n data points from scratch. What we've essentially done is transform the standard average filter into a moving average filter. Instead of averaging all data at once, resulting in a flat, unresponsive line, we now compute the average over a sliding window. This allows the estimate to adapt to changing data, smoothing out short-term fluctuations while still capturing long-term trends. While this is an improvement, there's still a drawback. As seen in the graph, the moving average introduces a delay. It lags behind the actual data. This delay occurs because each data point is given equal weight within the window, meaning recent changes don't immediately influence the estimate. This isn't ideal for our submarine scenario. We need an approach that both smooths out the noise while remaining synchronized with real-time changes. To address this, we introduce the low-pass filter. The key idea behind a low-pass filter is that it allows low-frequency trends to pass through while filtering out high-frequency noise. The main limitation of the moving average filter is that it assigns equal weight to all data points within its window, which causes a delay in response. Bringing this back to our submarine example, imagine we're in the heat of battle. If our filter blindly averages across 100 past data points, it reacts too slowly to sudden changes. Instead, we want a system that assigns more weight to recent data points. In the moving average filter, each term is weighted equally by 1 over n. This is not ideal for our submarine scenario. The most recent and least recent data points are given equal importance, but in reality, our latest position is way more important. To address this, we introduce the low-pass filter, which is defined as this expression right here, where alpha is a number between 0 and 1. At first glance, this resembles an averaging equation, but here alpha is a free parameter that we control. From now on, we will refer to x bar k as the estimate instead of the average. Now, how does this solve our problem of equal weighting? Let's expand on this equation step by step to reveal what's actually happening. First, we apply the same formula to the previous estimate, x bar k minus 1. Substituting this into our original equation, we get this. Expanding further and multiplying terms out, we get this. Since alpha is a value between 0 and 1, each successive term is weighted less than the most recent one. This means the latest measurement, x sub k, has the highest influence on our estimate, which is what we want. Depending on the value of alpha, we can control how responsive or smooth our estimate is. A higher alpha results in a smoother but less responsive estimate, while a lower alpha makes the estimate more sensitive to recent changes but makes it noisier. Everything we've done so far has laid the foundation for understanding how to refine noisy data over time. However, this is just the beginning. We still haven't even mentioned the Kalman filter, but we're getting close. Instead of introducing all the equations at once, I want to start broadly and gradually build towards the full picture. A good way to introduce the Kalman filter is to think of it as a low-pass filter, but with one key difference. Instead of using a fixed weighting for past and present data, like we have been using, the Kalman filter dynamically decides how much weight to give new measurements versus previous points. So basically, it's a low-pass filter with a dynamically changing alpha value. For example, if our sensor data is noisy, the filter trusts its previous estimate more, but if the measurements seem reliable, it adjusts to incorporate them more heavily. This adaptability is what makes the Kalman filter so powerful. So what is the big idea behind the Kalman filter? The Kalman filter is a way to find the best estimate of an unknown quantity or state or multiple variables over time, even when our measurements are noisy or uncertain. It does this using a two-step process. Step 1, prediction. The filter uses previous estimates and a mathematical model to predict where the system is now. Step 2 is the update step. It takes in new sensor data and adjusts its estimate to match reality more closely. By continuously refining its predictions and balancing trust between the model and new data, the Kalman filter improves its accuracy over time. Now let's go through the equations of the Kalman filter. First, let's cover the prediction state and the error covariance. Let's assume that in our submarine, we want to predict what our depth is using an ultrasonic sensor. The problem is that we can't rely solely on the sensor. Its readings contain noise, and our depth also depends on our previous depth. In other words, we can think of our current state as a function of our previous state plus the new measurement we take in. With each estimate that we make, whether it's for position, velocity, or depth, whatever, there is always some level of uncertainty that comes with it. This is why the Kalman filter consists of two steps, prediction and update. Why do we need a prediction step? Why not just estimate it from the get-go? Because it allows us to maintain a continuous estimate of the system state even when no new measurement is available. If we skipped the prediction step, the filter wouldn't function properly in real-world scenarios, where a sensor readings can be noisy, delayed, or even missing. A key part of this process is the error covariance, denoted as pk. This represents how uncertain we are about our estimate, x hat k. A large pk means there's a high level of uncertainty, while a smaller pk indicates that we're more confident in our estimate. Since we know that the Kalman filter is recursive and that the state that we want to predict depends on the previous step's estimate, we can begin with a simple equation like this one, where the prediction is simply equal to the estimate from the previous time step. Surprisingly, this is very similar to what the real equation is. However, we are missing a quote constant. It's not really a constant, but you can think of it like that. This is the equation. A is called the state transition matrix. It describes how things change over time. Its job is basically to describe how the system evolves from one time step to the next. It's a matrix that predicts where an object should be based on its past movement. For our predicted error covariance, we know that, like the state, it depends on its estimate from the previous step. However, the state transition matrix A also shows up here, but it's slightly more complicated. This is the equation. A by itself is used to project the previous error covariance into the next step, and AT ensures the correct transformation of uncertainty in state evolution. But don't worry too much about this. We are still missing one thing: noise. Q accounts for unknown factors affecting the system. Here's an alternative way to learn about the prediction step by looking at the system model equations. Let's start with the state transition equation, where A is the state transition matrix and WK is the state transition noise. It is an n by 1 column vector and it represents uncertainty in the system dynamics, for example, like ocean current affecting a submarine's motion. The measurement equation is this, where ZK is the measurement vector. H is the measurement matrix mapping the actual state xk into measurement space, and Vk is the measurement noise. It is an n by 1 column vector and it represents the random error in sensor readings. Now let's learn about computing the Kalman gain. When we transition from the moving average filter to the low pass filter, which remember filters out high frequencies, noise, we eliminated the delay in our approximation by manually choosing an alpha value. This parameter determined how much weight we assign to recent data points within our n window. In the Kalman filter, however, we don't manually select alpha. Instead, the filter dynamically determines the optical weighting at each step. As the data evolves, the Kalman filter continuously calculates a gain factor, or like a constant, that decides how much we should trust the new measurement versus our prediction. This dynamic weighting is represented by the Kalman gain K sub K, which is computed at each step. If the sensor data is highly noisy, the filter will rely more on its previous predictions, but if the new measurements seem reliable, it will incorporate them more heavily. The exact computation of the Kalman gain is quite complicated and it's very involved, so I won't go into full derivation here. However, its fundamental role is to optimally balance our trust between the predicted state and the incoming measurement that we take in. I will not go into how to calculate the Kalman gain exactly, but here's the full equation, where R and H are yet more matrices. H is different to A. Instead of helping to predict how the state evolves over time, which wouldn't really be useful here, H is the measurement matrix. Its job is to translate the state into observable sensor data. And recall, the Kalman gain comes in handy in the estimation step. So let's break that down now. The final step in the Kalman filter, which is computing the estimate and the error covariance, is crucial. But it's important to remember that the filter is recursive. This means that what we compute here becomes the initial value for the next step. Let's return to our submarine example. If we want to determine our depth given both our prediction and a new measurement, how would we estimate it? The estimate is a function of the prediction, the Kalman gain, and the difference between the measurement and the prediction. The error covariance, which represents our uncertainty, depends on both our prediction and the Kalman gain. Kalman gain decides how much to weigh the measurement versus the prediction based on their uncertainties. If the measurement is noise, we trust the prediction more, and vice versa. If the prediction is uncertain, a larger error covariance, we trust the measurement more. That is what we mean by the Kalman gain being multiplied to the difference of the measurement and the prediction. When we compute the estimation of our error covariance, which tells us how far off our estimation of the state is from the true mean, we know that it depends on its prediction, of course, and then we try to reduce the uncertainty using the Kalman gain. If K is large, we trust the measurement more and more uncertainty is removed. If it's small, we trust the prediction more and less uncertainty is removed. Let's use the same example from earlier. Imagine you're deep underwater piloting a submarine through unpredictable ocean currents. Your goal is simple: accurately track your depth to avoid obstacles and navigate safely. However, two major challenges stand in your way. First, the ocean's movement is not entirely predictable. Currents can push your submarine slightly off course in ways you can't fully account for. Second, your onboard's depth sensor, while useful, doesn't provide perfect readings. Its measurements fluctuate due to noise, making it unreliable if taken at face value. Given these uncertainties, how can you determine your actual depth at any given moment? Instead of only relying on this noisy sensor, we need a smarter approach, one that continuously refines our estimate by balancing past knowledge with new observations. This is exactly what the Kalman filter is designed to do. By combining predictions of where we should be with the latest sensor readings, it allows us to arrive at the best possible estimate of our submarine's depth, improving as more data comes in. Let's now break this down step by step and apply the Kalman filter to our submarine's depth estimation problem. Before running the Kalman filter, we define its key values. A and H are both equal to 1 for simplicity's sake. The rest of the values are arbitrarily chosen. They don't really need to be that. The system model is given by these two equations from earlier, where xk's are true depth, which we don't actually know, but we use a Kalman filter to approximate. Zk is our sensor measurement, which comes with noise. Wk can be approximated with a normal distribution of mean 0 and standard deviation q, and it represents the random ocean drift noise affecting our movement. Vk is also approximated with a normal distribution, but this time with standard deviation r, and it's our sensor noise affecting measurements. All of this gives us the simplified model here. Xk is equal to xk minus 1 plus wk, and zk equals xk plus vk. Now I'm going to show 5 time steps of the Kalman filter. Here are the final results that we got. Here are some very basic graphs of what we just did. Initially, the filter starts with high uncertainty, but as more data points are processed, the error covariance pk decreases, meaning our estimates become more confident over time. The Kalman gain, k, dynamically adjusts how much we rely on the measurement zk versus our predicted estimate x hat minus k. When the sensor is unreliable, the filter leans more on predictions, and when the sensor is accurate, it weighs the new data more heavily. The beauty of the Kalman filter lies in its recursive nature. Rather than storing vast amounts of historical data, it only keeps track of the latest estimate and its associated uncertainty. This makes it computationally efficient, while maintaining a high degree of accuracy. At its core, the Kalman filter embodies a powerful principle. Even in the presence of uncertainty, we can make informed predictions and continuously improve our estimates by intelligently integrating past knowledge with new observations. Understanding this technique not only gives us a practical tool for solving engineering problems, but also teaches us a mindset of thinking probabilistically, and it teaches us to adapt to new information and make better decisions in an uncertain world. Thank you for watching.